In the 19th century, when mathematics was still limited to numbers and geometric shapes, a solitary man dared to imagine something completely new, an abstract system capable of describing any dimension of space. His name was Hermann Grassmann, a modest, almost anonymous professor who conceived one of the most revolutionary ideas in the history of science: vector algebra. Ignored by his contemporaries and forgotten by academia, Grassmann developed concepts that would only be understood decades later, fundamentals that today underpin modern physics, engineering, and the very mathematical language we use to describe the universe. This is the story of a thinker who saw further than his time could reach, the silent genius who anticipated the future of mathematics. The greatest mathematicians of all time. Episode 20. Hermann Grassmann.
Hermann Grassmann was born on April 15, 1809 in Stettin, Prussia, now Szczecin, Poland, and died on September 26, 1877 in the same city, now Germany, present-day Szczecin, Poland. Hermann Grassmann's father was Justus Günther Grassmann, and his mother, Johanne Luise Friederike Medenwald, the daughter of a pastor from Klein Schönfeld. Justus had been ordained a pastor, but took a position at the Stettin Gymnasium as a mathematics and physics teacher. He was a brilliant scholar who wrote several textbooks on physics and mathematics, as well as conducting research in crystallography. Johann and Justus had 12 children, Hermann being the third. Hermann's brother, Robert, also became a mathematician, and the two collaborated on many projects. As a young man, Hermann was educated by his mother, a cultured woman. Later, he attended a private school before entering the Stettin Gymnasium, where his father taught. Most of the mathematicians in this archive impressed their teachers from a young age, but surprisingly, despite having excellent educational opportunities in a family with a strong inclination towards education, Hermann did not excel during his early years at the gymnasium. His father thought he should dedicate himself to manual labor, such as a gardener or craftsman. Hermann, however, found pleasure in music and learned to play the piano. As he progressed through school, his performance gradually improved, and when he took his final high school exams at the age of 18, he came in second in his class. Having demonstrated himself to be, at the very least, a quite competent student, Hermann decided to study theology and went to Berlin in 1827 with his older brother to study at the University of Berlin. He studied theology, classical languages, philosophy, and literature, but does not appear to have studied mathematics or physics. Although he apparently did not have formal university training in mathematics, it was this subject that interested him upon returning to Stettin in the autumn of 1830, after completing his university studies in Berlin. Clearly, his father's influence was important in guiding him down this path, and he decided at that time that he would become a teacher, but he was determined to conduct mathematical research on his own. After a year dedicated to mathematical research and preparation for the qualifying exams for teaching in secondary schools, he traveled to Berlin in December 1831 to take the necessary exams. His performance must not have been satisfactory, as the examiners only approved him to teach at the lower levels of a secondary school. He was told that before he could teach at more advanced levels, he would need to retake the exams and demonstrate a much greater knowledge of the subjects for which he had registered. In the spring of 1832, he was appointed assistant teacher at the Stettin Gymnasium. It was around this time that he made his first significant mathematical discoveries, which would lead him to the important ideas he would develop a few years later. In the preface to his work, Theory of Linear Extension, a New Branch of Mathematics, 1844, Grassmann described how he was led to these ideas starting in 1832.
In 1834, Grassmann took the first-level theology examinations established by the Lutheran Church Council of Stettin, but, although this could have been his first step towards becoming a Lutheran minister, he went to Berlin in the autumn of that year to take up a teaching position in mathematics at the Gewerbeschule. The vacancy had arisen because the previous teacher, Jakob Steiner, had just been appointed to a chair of mathematics at the University of Berlin. Grassmann spent only 1 year at the Gewerbeschule before a new opportunity arose in his hometown, Stettin. A new school, the Otto-Schule, had just opened, and Grassmann was hired to teach mathematics, physics, German, Latin, and religious studies. He was only qualified to teach at a basic level, which partly explains the wide range of topics he taught. For the next 4 years, Grassmann took his teaching very seriously, but managed to find time to dedicate himself to mathematical research and also to prepare for further examinations. In 1839, he passed the second-level theology examinations established by the Lutheran Church Council of Stettin, and in 1840, he went to Berlin to take examinations that would allow him to teach certain subjects at the highest level of the gymnasium. From then on, he was able to teach mathematics, physics, chemistry, and mineralogy at all levels of secondary education. In fact, the examinations that Grassmann took in 1840 were significant for him in another way. He had to submit an essay on the theory of tides as part of the examination. He based the theory on the work Mécanique céleste by Laplace and Mécanique analytique by Lagrange. But he realized that he was able to apply the vector methods he had been developing since 1832 to produce an original and simplified approach. His essay on theory of tides was 200 pages long and introduced, for the first time, an analysis based on vectors, including vector addition and subtraction, vector differentiation, and the theory of vector functions. Although his essay was accepted by the examiners, they did not recognize the importance of the innovations introduced by Grassmann. On the other hand, the essay showed Grassmann that his theory was widely applicable, and he decided to dedicate as much time as possible to developing his ideas on vector spaces. Of course, Grassmann could not dedicate much time to research, as he was a dedicated teacher who wanted to commit himself fully to his work. He wrote several textbooks, 2 of which were published in 1842, one on spoken German and the other on Latin. After writing these books, he dedicated himself entirely to writing Theory of Linear Extension, a new branch of mathematics. He began in the spring of 1842, and by the autumn of 1843 had already completed the manuscript. It was published the following year. In this work, which should be considered a masterpiece of originality, he developed the idea of an algebra in which symbols representing geometric entities, such as points, lines, and planes, are manipulated using certain rules. He represented subspaces of a space by coordinates, leading to the mapping of points of an algebraic variety, now called a Grassmannian.
Fearnley Sander writes in Hermann Grassmann and the Creation of Linear Algebra about the vector methods that Grassmann established in this work and further refined in 1862. Starting with a collection of units, he effectively defines the free linear space that they generate. That is, he considers formal linear combinations where each combination is a real number. He defines addition and multiplication by real numbers in the usual way today, and formally demonstrates the linear space properties for these operations. He then develops the theory of linear independence in a way surprisingly similar to the presentation found in modern linear algebra texts. He defines the notions of subspace, independence, span, dimension, join and intersection of subspaces, and projections of elements onto subspaces. He is aware of the need to demonstrate the invariance of dimension under change of basis and does so. He demonstrates the Steinitz exchange theorem, named after the man who published it in 1913. Among other results, he shows that any finite set has an independent set with the same span, and that any independent set extends to a basis, and demonstrates the important identity dimension of U plus W equals dimension of U plus dimension of W minus dimension of U intersect W. He obtains the formula for change of coordinates under change of basis, defines elementary transformations of basis, and shows that every change of basis, equivalently in modern terms, every invertible linear transformation, is a product of elementary ones. Grassmann also realized that once geometry is placed in this algebraic form, the apparent restrictions of three-dimensional space disappear. Grassmann wrote in the 1944 theory of linear extension, "If two different rules of change are applied, the set of elements produced forms a system of the second step. If a third independent rule is added, a system of the third step is obtained, and so on." The theory of space can serve as an example. The plane is the system of the second step. If a third independent direction is added, the entire infinite space, third step system, is produced. Here, one cannot go beyond three independent directions, rules of change, while in the pure theory of extension, their quantity can increase to infinity. Grassmann invented what is now called exterior algebra. This was combined with Hamilton's quaternions by Clifford in 1878. Clifford replaced Grassmann's rules. Clifford algebras are used today in the theory of quadratic forms and in relativistic quantum mechanics. Clifford algebras appear together with Grassmann's exterior algebra in differential geometry.
What did mathematicians think of this revolutionary text? Unfortunately, it was too far ahead of its time to be appreciated. Mobius did not understand the importance of Grassmann's approach and refused to write a review. As a consequence, the book was largely ignored. Grassmann, however, continued to apply his new concepts to other situations, believing that once people saw how the theory could be applied, they would take it seriously. He published New Theory of Electrodynamics in 1845 and wrote several articles with applications to algebraic curves and surfaces over the next 10 years. He received greater recognition for a work produced in 1846. Möbius suggested that he compete for the prize offered by the Fürstliche Jablonowskischen Gesellschaft for works that solved a problem initially proposed by Leibniz to establish the geometric characteristic without using metric properties. Grassmann submitted Geometric Analysis and the Characteristics of Leibniz, which received the prize on July 1, 1846. However, it wasn't all good news for Grassmann, as his work was the only one submitted, and Möbius, one of the judges, criticized the way Grassmann introduced abstract ideas without providing the reader with an intuitive hook to understand them.
Grassmann felt somewhat wronged for producing highly innovative mathematics, which he considered important, while still teaching in secondary schools. In fact, although he had been in Stettin since his first appointment to the Otto School, he had been transferred first to the Stettin Gymnasium and then to the Friedrich Wilhelm School due to the city's educational reorganization. In May 1847, he received the title of Oberlehrer at the Friedrich Wilhelm School and, in the same month, wrote to the Prussian Ministry of Education requesting his name be included on a list of candidates for university positions. The Ministry of Education asked Kummer for his opinion on Grassmann, who read his award-winning essay, Geometric Analysis, and reported that it contained laudably good material but poorly expressed. Kummer's report ended any hope Grassmann might have had of obtaining a university position. It is interesting to note how many renowned mathematicians failed to recognize that the mathematics presented by Grassmann would become the fundamental basis of the discipline in 100 years.
The years 1848 and 1849 were marked by revolutions. The fall of King Louis-Philippe of France in February 1848 was the trigger for revolutions in the German Confederation. Movements were made towards the political unification of Germany, but fierce disputes followed over how the country should be governed. During this revolutionary period of 1848-1849, Grassmann, together with his brother Robert, published a weekly political newspaper. His political position was to push for the unification of Germany as a constitutional monarchy. After writing a series of articles on constitutional law, Grassmann became increasingly dissatisfied with the political direction the newspaper was taking and disassociated himself from it. In early 1849, he married Therese Knapp, the daughter of a landowner, on April 12th. They had 11 children, 7 of whom reached adulthood. One of his sons, Hermann Ernst Grassmann, received his doctorate in 1893 with his thesis, Application of the Theory of Extension to the General Theory of Spatial Curves and Curved Surfaces, written under the supervision of Albert Wangerin at the University of Halle-Wittenberg. He later became a professor of mathematics at the University of Gießen. In March 1852, Grassmann's father, Justus, died, and later that year, Grassmann was appointed to fill his father's former position at the Stettin Gymnasium. This meant that, although he was still teaching at a secondary school, he now held the title of professor. It is worth noting that 2 of Grassmann's sons, Justus and Max, eventually became teachers at the Stettin Gymnasium. Having failed to gain recognition for his mathematics, Grassmann turned to one of his other favorite subjects, the study of Sanskrit and Gothic. In fact, during his lifetime, it can be said that he gained more recognition for his study of languages. By demonstrating that Germanic was in fact older in a phonological pattern than Sanskrit, Grassmann undermined the position of Sanskrit as the oldest language attainable in Indo-European linguistics. With this demonstration, Grassmann also undermined the notion that language developed from an analytical structure to a synthetic structure through the combination of simple words without altering their form to create new words. But Grassmann also studied problems in physics, in particular, publishing a theory of color mixing in 1853 that contradicted the one proposed by Helmholtz. However, in the middle of the following year, he returned to mathematics and his theory of extension, deciding that instead of writing a second volume, as he had originally planned, he would completely rewrite the work in an attempt to have its importance recognized. In fact, despite having written a work that today seems to us in the style of a modern textbook, Grassmann failed to convince the mathematicians of his time. Perhaps he was so convinced of the importance of the subject that he failed to make the effort to present it to skeptical readers. Certainly the book, Theory of Linear Extension, completely processed in strict form, the work published by Grassmann in 1862, fared no better than the first version of 1844.
Disappointed at failing to convince mathematicians, he turned again to research in linguistics. In this area, he was much more successful and was honored for his contributions, being elected to the American Oriental Society and receiving an honorary degree from the University of Tübingen. He returned to mathematics in the last years of his life and, despite failing health, prepared another edition of the 1844 Ausdehnungslehre for publication. It was published, but only after his death. Grassmann died of heart problems after a period of ill health. Grassmann's mathematical methods were slow to be adopted, but eventually inspired the work of Élie Cartan and have since been used in the study of differential forms and their application to analysis and geometry. Others who were directly influenced include Hankel, Peano, Whitehead, and Klein. Much of Peano's contributions were, as he himself acknowledges, based on Grassmann's ideas. As A.C. Lewis writes, "It seems to be Grassmann's fate to be rediscovered from time to time, each time as if he had been practically forgotten since his death in 1879. Fernley Sander writes in Hermann Grassmann and the Creation of Linear Algebra, "As Newton said, all mathematicians stand on the shoulders of giants, but few have come as close as Hermann Grassmann to creating, single-handedly, a new area of study. Time, which so often erases, is also capable of correcting. And today, more than a century later, we recognize in Hermann Grassmann what he always was, one of the most original and visionary thinkers in the history of mathematics." If this video helped you rediscover the legacy of Hermann Grassmann, please share this content with other educators and researchers. Subscribe to the channel to continue exploring the stories that shaped scientific thought and help us keep alive the memory of the great names that transformed human knowledge.